Hey, welcome back to StackIt. Just in the previous video, we got stuck a little bit at implementing the principal variation, which is returning the best move sequence. In between those videos, I took a deep breath and I actually read up on how it's usually done in chess engines, and I found that initially in the series I plan to do that when we implement hash tables, because usually you can kind of get it out of the hash table easily. Spontaneously I decided against it because I kind of thought it's nice if we can already display a couple of things in our performance test. I now fix it for now. So, and I did some minor cleanups. So one thing I did is I inserted a debug flag in our AI, which we can use for debugging, and I'm going to show in a second what that would trigger. It would trigger that if we run the AI, we print the moves, the score, the depth, and the current player, and maybe we will also print the board, so it's easier to understand what's happening. And then it waits for our input, and it also prints when we found the best move. This is one thing. And for principal variation, the way it works is now we initialize principal variation to nothing, and in every step of our search tree, we build a local principal variation. This will be an empty array, and for every step that we do, we will return the principal variation that we found down the tree. And let me just see, where is this initialized? And the principal variation inside, these ones need to go bottom, I like this more anyway. And the principal variation in each tree is the current best move plus the local principal variation returned from down the tree. And then we return this. And in order to not return this back to the user, we actually catch it here in our best move, set it to our self-principal variation, and then only return the move in the score like we had it before. This looks now like this. One thing I should do so that we can actually cancel this without any problems is we where do I put it? So I want to rapid try catch and then just catch the keyboard interrupt and not print the stack trace, because we want to keyboard interrupt this. Try. It just cancels. We don't care about, do we? No, if something breaks now. Maybe we only catch keyboard interrupts. Yeah. I wonder if I have to import this from somewhere or not. No, it works. So now we can cancel this without having the stack trace, so it's easier to read the stuff. And you can see, okay, we find 1-0 as best move. This is basically assuming, oh, we throw over this pile of 4 and then we win. But if we look one move deeper, we find, oh, if we play on 1-0, then it sucks, and then it would play on 0-0, and red would play on 2-0 because there's no deeper looking. And yeah. What else is happening here? Let's go down here. Yeah, this can go. This is a confusing output that you see on the bottom. Okay, AI is not defined. Print. Forgot to comment out the print. Okay. No, yeah. Okay, this is what I want. Okay, in this episode, we will actually implement AlphaBeta windows. Let's start with this. So, the idea behind AlphaBeta is the following. Right now, what we're doing, we're searching for every possible move. But AlphaBeta introduces the idea that we do not need to search all possible moves in case we already found a move that is pretty good, and we search a move that is worse than this. We can assume that, for example, our opponent would never play into this branch. So let's say we have two moves that we are searching. One is really good for us and one is not so good for us. And we know that our opponent would definitely always play the one that is not so good for us, because our opponent tries to minimize what we are doing. So if we find out that a move is better than the currently worst one, we can immediately stop searching in that tree. One thing is, here I searched the principal variation. There's this chess wiki. It seems to be actually down now. But in Google Cache you can still find it. And one thing we can see here is actually, let's just search AlphaBeta pruning and take the Wikipedia article or something, and then read it real quick. So this is basically what we know. They call it AlphaBeta now, and then if the depth is 0, it's a terminal node. We return the heuristic value of the node. Here it's actually not like we wanted. Yeah, let's search this one. Is this what we want? No, this is kind of what we want. Kind of. So I say kind of because they already have move ordering. We're not doing this yet. The idea is, once we have these AlphaBeta windows, they are called, that help us to decide whether we should cut off early and not search a specific move. Once we have that, we want to make sure we order our moves in every step, so that the most promising move will be played first, because then we can cut off the whole rest of the tree. How does this work? We introduce two more parameters, alpha and beta. We pass them down, negated and reversed, because what for me would be a high cutoff is a bad cutoff for my opponent. Let me read this real quick. Yeah, this is even more complicated, but this is basically what it amounts to. So, okay, depth alpha beta, then plus minus beta. Alpha. This is slightly different from what we have. So I need to think a bit how we put it in. Let's go here and close this really quick. So should we make a new file maybe and copy most of this stuff so that we can keep our old algorithm, and then maybe we can let them play against each other. AlphaBeta. I think so. AlphaBeta get initialized to big values, plus minus infinity, minus plus. Sorry. I just take pretty big values. And next we I could use NumPy for all of that. Next we need to minus beta. That's correct, right? Minus beta minus alpha. And then here if the score is the bigger score out of both of them, okay, and then alpha is the bigger one, either alpha or the value, and if alpha is bigger than beta, the score then we can cut off. Let's check this here. So alpha score. Oh, this one assumes that they are ordered, doesn't it? I know. This means here we already found a move that is worse than we found in another part of the tree. Game pi. Let's just see. Okay, you can already see this is much faster than before, but does it still give the same results? 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0. Yeah, this was surprisingly easy to implement, and now you can see you can easily search up until depth 8 within 10 seconds, or maybe 11 seconds, which is already vastly better than maybe 5 or 6. And we search way less nodes. And here we know that after 9 moves, we are we will be ahead by 9 points in this board configuration. And let's see. One thing I want to do now. Approved. And let's rewrite this a bit. For now. And then we search AlphaBeta first. And here range 6 or something enough for 7. And then let's change the board slightly. What happens if we have a 4 here instead? So first is AlphaBeta search and second is MinMax. You can see MinMax is way slower. They find the second moves, the same moves, and it seems to be a pretty even position. Let's see if we go deeper. We should think about whether we want to implement a quiet send search where we would play all possible fallovers in the last moves until it's quiet. It's a pretty even board. I actually wonder if on a bigger board, for example, you can already see right now there's not much the engine would find as an advantage. It's basically even. And I wonder if on bigger boards it will be really hard to find any good strategies with this because we cannot search deep enough to find any interesting patterns. Okay, let's see what we changed. We changed our perf function. We changed the main function a little bit, and we added moves made, the principal variation, and the debugging. Let's add the AlphaBeta as well. PV lens. Maybe we can try and play our AI for the next 5 to 10 minutes on a little board. Let's just make it a 3x3 and see how ugly this will be. Oops. R0. So this will be an empty board, and we run the game, and board move, and we will take a AlphaBeta AI. AlphaBeta. Let's limit it to 6 for now and see if move board. And then, yeah, let's see. Okay, let's just go into the middle. Oh. Move. Ah. Okay. Here we, of course, want to. Wow. Okay, let's see what it does if we set next to it. I think the best move here would be to increase one, yeah. And now we should I'm just thinking now, he could force me to throw over my middle. Okay. And so, bam. What happened? What happened here? Okay. My AI definitely thinks it lost and then it didn't return a move. No? It said it would move. So after I play this move, it's done. And my AI lost. I think there would have been. So first off, print E, and then there was a winning player. So I think we should do this, and then let's see if we can search a bit deeper. This may take super long now. Probably another thing we can do to make our AI much better is instead of just counting the number of pieces, also counting territory somehow. One issue a little bit is that we already need 8 moves to just get 2 pieces of 4, which just kills the AI. It can now just look basically to where it gets interesting. So maybe one thing we could do to the game is if the field is empty, instead of increasing by 1, we could increase by 3. Just for the sake of the AI. Okay, 8 seems to be too long. And I think we still have quite some room up. I'm not sure how deep we will actually go eventually, but like the implementation of the board and everything is far from perfect. We could do something like this, and then . What do you have? Test move. No. Yeah, this kills the tests. So much for the idea, but later on the tests will be very helpful when we try to rewrite the board in NumPy. It's not even testing everything, it's just some rudimentary tests. Okay, maybe 10 is too much. No. Let's take the corners. Ooh. Ooh. Ooh, I'm losing, huh? -8. No, it thinks it's losing, isn't it? So, for example, here, I think what it should try to do is make me throw my blocks over. If okay, up here it thought it's going to lose by -11, and here it's going to lose by -7. I can win this race. I see. Ouch, ouch. Suddenly I'm losing. But it's very interesting that up here it thinks it's only -1, and then down here it suddenly finds that it's winning. There's just one move difference, and I don't necessarily see what could have done up here that makes me be -1. So I assume there's probably still some issue. Anyway, let's call it a night. It's kind of late, and tomorrow is Monday. A couple of things. I kind of really don't like my code so far. It's got pretty dirty already, and I should think twice if I don't have any serious issues in here. One thing I will definitely do is I'm gonna save this board here, here, where it thinks that it's a -1, and then I'm gonna figure out why it didn't see immediately that it would win, because I don't know. There's nothing I could have done differently than this one move, and I don't think that it thinks it will win in more than 6 moves. Because from here on out it's pretty straightforward. You throw this one over, taking my 3 away to 4, and no matter where I put my stone, I'm behind. So anyway, thank you for watching, and see you in the next episode.